down Main Street. You're relaxed and feeling good. Next thing that you know, you'll see an octopus.
Let's go!
On sideways, swinging through the stars. Take a left at your intestine. Take a second right fast bus.
On the magic school bus.
Alligator? No, it's true. I'm on the magic school bus. Frank a blade, doom, doom. I'm on the magic school bus. Start the river of lava. Running on the magic school bus.
In class, today we are learning about the nature of sound. A sound wave is created when an object vibrates, it collides with nearby molecules in the air, transferring energy to them. The cycle repeats until the energy is used. Sound is a compressional wave. If you were paying attention in class before, you should know what that is. But for those who don't know, it's a matter of moving back and forth in the same direction. The speed of sound changes. It moves at different speeds in different materials. Yes, Emma.
What's the speed of sound through air?
347 meters per second.
Well, what's the speed of sound through water?
1,498 meters per second. Jack.
Why does sound travel at different speeds through different materials?
That's a good question. Here, let me show you. There will be three parts to this. One for solids, liquids, and gases. You will represent the particles in each material. Let's start with gas. Here, hold this. And pass it down the line. Notice how the bucket took a while to get down the line? Now everybody take a step in closer. Now we're representing, okay. Perfect. Now we're going to be representing liquids. Pass it down the line. Perfect. Notice how the bucket took less time? Now everybody stand shoulder to shoulder. Alright, now pass the book. Perfect. That was the fastest. So just like you guys passing the bucket down, the particles bumped into each other and transfer energy.
Question.
Yes.
How can we hear the sound waves?
Yes, I'm glad you asked. This is a perfect opportunity to take a field trip.
I'm on the magic school bus. Start the river of lava. Running on the magic school bus.
Our ear is made into three parts, the outer, middle, and inner ear. The visible part of your ear, the ear canal, and the eardrum make up the outer ear. Gathering sound starts with the outer part of your ear, which helps capture sound. The sound then goes into your ear canal and vibrates your eardrum. When the eardrum vibrates, it sends the sound vibrations to the middle ear. The hammer, anvil, and stirrup make up the middle ear. When sound passes through the middle ear, it is amplified by the lever system the bones make. The vibrations are sent to the inner ear. The inner ear is made up of many coagula. These small spiral-shaped structures contain tiny hair cells. These hair cells convert vibrations into nerve impulses and get sent to the brain.
That's cool.
Now that we have the nature of sound down, now we can go into the properties of sound.
So wait, sound owns property?
No, not like that. It's more like intensity and loudness. Intensity can be measured by finding the amount of energy that flows into a certain area in a specific amount of time. For example, when you have an aux plugged in and you're jamming out and the volume is really loud, the sound waves have higher intensity. Or say you're babysitting and your sibling is sleeping in the back seat. You don't want to wake him or her up, so you have the volume really low. This is when low intensity sound waves. The larger the sound waves, the greater the intensity is. So when I yell like this, the intensity is higher. And when I whisper like this, loudness is just a perception of how loud something is. Sons, people vary in perception of loudness. It has a scale measured in decibels.
Oh, I get it. So when intensity is higher, sound travels faster?
Great question, Emma. You might think so, but speed and intensity are not related. No matter how loud or quiet something is, it will always travel at the same speed. Okay, for the last property, we'll have to go to the racetrack. Yes!
School bus. Start the river of lava. Running on the magic school bus.
On the International Speedway, I can explain the Doppler effect. It involves a moving object and a stationary observer. The Doppler effect is a change in pitch wave frequency due to moving wave sound. For example, a race car zooming by you. As it approaches you, the pitch increases, and when it flies by, the pitch lowers. The race car sends out sound waves as compression and rarefaction waves. Compression waves are sent out by the car and heard by the observer. The sound waves get bunched up in front of the car, which makes a higher frequency. When the car passes you, you hear the spread out or lower frequency waves, lower pitch. It was brought to you by the company Thirst No More. This is our new product, Thirst No More. Are you ever tired of not being able to perform at your best or being worse than the competition? Well, we have the product for you, Thirst No More. Buy your Thirst No More product. Call this easy, accessible number. 1-800-888-776-577. Sydney Opera House. Famous for its iconic architecture and wonderful acoustics. We will start by learning pitch. Pitch is how high or low a sound seems to be. A pitch is where its a wave frequency are related. So if you change the pitch, you are also changing the wave frequency. Now, does anybody remember what frequency is?
Ooh, I know. It's the measure of how many wavelengths pass a particular point each second.
Perfect. Most people can hear frequencies above 20 hertz and 20,000 hertz. Anything above ultrasonic waves, some animals can hear these ultrasonic waves, such as dogs. Frequencies below 20 hertz are created by all things that vibrate slowly, like wind and earthquakes. Another type of frequency is natural frequency. Every material has a particular set of natural frequencies at which it vibrates. Each piano string has its own natural frequency. These frequencies can be amplified by resonance. Resonance occurs when a material or an object is made to vibrate at its natural frequencies, by absorbing energy from something that is also vibrating at those frequencies. For example, Jack, when you play your saxophone, the vibrations of the mouthpiece reed causes the instrument to absorb energy and vibrate at its natural frequencies, making the instrument louder. Nice job. Oh, no, this reminds me of something else. Sound quality. It describes the difference among sounds of the same pitch and loudness. When Lucy plays her flute and you play the piano, even with your eyes closed, you can still tell the two apart. That means they have different sound qualities. It's very similar to overtones.
What's an overtone?
An overtone is a vibration whose frequency is multiple of the fundamental frequency. Now, you may be wondering what a fundamental frequency is. Let me explain. An instrument plays many different frequencies at once, yet you only hear one note. The main tone that you hear is called the fundamental frequency.
Doesn't a cello create overtones?
Yes, it does. The higher the frequency, the more overtones there are. A cello also uses what is called a resonator. A resonator is a hollow chamber filled with air. This chamber amplifies the sound when the air inside of it vibrates, like this.
These saxophones don't have a resonator. How do they make sound?
Wow, you guys are just full of amazing questions. Well, Jack, brass and woodwind instruments rely on the vibration of air to make music. The air flows through the tubing of the instrument, which makes itself a resonator. So both you and Lucy need to use air to make noise. The length of vibrating tube air determines the pitch and sound produced. So when Lucy covers her flute holes, all the finger holes in her flute, the length of the instrument or resonator increases, making the notes lower. There are also instruments with large resonators. Some of these are percussion instruments. Percussion instruments have a membrane stretched over the resonator. When the membrane is struck like this, it makes the air inside of the resonator vibrate. Some percussion instruments have a fixed pitch, but others can have a pitch that changes by tightening or loosening the membrane.
We hear that pulsing noise when we tune.
This happens when frequencies are just slightly off. The pulsing noise is called a beat. Two compression waves amplify each other, increasing the loudness of the two rarefaction waves overlap each other, decreasing the loudness. This noise of increasing and decreasing loudness is what you hear as the pulsating noise. If two instruments with similar sound quality are in tune with each other, no beats should be heard. Since we are still here in the Opera House, we might as well take advantage of the wonderful acoustics.
What are acoustics?
Let me demonstrate. When I hit this drum, you shouldn't be able to hear an echo. Listen. The reason you cannot hear the echo is because the engineers that specialize in acoustics or study of sound know that such as a blanket absorbs the sound better than a brick wall. Okay, I think we've got our use of the Sydney Opera House. Time to head back to the classroom.
On the Magic School Bus.
What were we talking about again?
Acoustics.
Acoustics.
Oh yes, acoustics. This reminds me of reflection of sound waves. It's very similar but used in different ways. Echolocation is the process of locating objects by emitting sounds and interpreting the sound waves that are reflected back. Animals like bats use this to navigate in the dark. They make small ultrasonic clicking noises. Some of the waves bounce back on the bat. Then the bat can determine the location of the object. Dolphins also use this technique to hunt. Jack.
Isn't echolocation used in submarines?
Yes, but that's called sonar. Sonar is a system that uses reflection of underwater sound waves to detect objects. Since more detail can be revealed by using sound waves of a higher frequency, sonar uses ultrasonic waves. It goes like this. A sound wave pulse is sent out through the water and is reflected when it hits something solid. A sensitive underwater microphone called a hyperphone picks up the reflected signals. The cool part about this is since the speed of the sound through water is known, you are able to calculate the distance between you and the object by measuring the time passes between emitting the sound pulse and receiving the sound pulse. This idea was first used to avoid icebergs, but now it has many uses, one of which is mapping the ocean floor.
Okay, so when I go fishing and I use a fish finder, is that device using sonar to locate the fish?
That is correct. There is even more to high-frequency waves than just echolocation and sonar. Ultrasonic waves are used to remove dirt from jewelry and glassware. Another important use of ultrasonic waves is through medicine. Scientists send waves to a specific part of a patient's body. Reflected ultrasound waves are used to detect the condition such as pregnancy, certain types of heart disease, and cancer.
So when doctors take x-rays, they are using ultrasonic waves?
Yes, they are. A medical ultrasonic technique detects the ultrasonic waves towards a target area in the patient's body. These waves reflect back and create electric signals. The computer receives these electric signals and converts them into video images, called sonograms. These are used to examine many body parts, such as the heart, gallbladder, liver, pancreas, kidneys, and much more. Now that's all for today's lesson.